Hi guys, in this video we are looking at the reaction quotient. Now reaction quotient has two important functions. The first one is to determine the shifting of equilibrium position when there is a change in concentration. Now you realize that this is very similar to the Shuttle Principle, right? The Shuttle Principle also allows us to predict how the equilibrium position change when there is a change on the system. But the difference is that in the Shuttle Principle, we go for the qualitative approach. We simply predict using the change, okay, and then we try to counteract the change, right? But for reaction quotient, we go for a quantitative approach. We will calculate the so-called reaction quotient, and we compare it with the equilibrium constant, and so we can predict or determine how the position change. So it is more of a quantitative approach, and actually later on, we also know that in some situation, the Shuttle Principle fails to predict the change, whereas reaction quotient allow us to do the prediction, and that one will be discussed later. So that would be the first function of reaction quotient. Now the second function, the second purpose is something what the Shuttle Principle cannot do, is when we start off with a non-equilibrium mixture. Now imagine you have some reactant, some product which combines to form an equilibrium system, and you simply dump them into a beaker. And the question is whether or not you predict there will be a faster forward reaction or a faster backward reaction. You realize that using the Shuttle Principle, you don't know it. You don't know because there is no change occurs on the equilibrium mixture. Now you realize that for the Shuttle Principle, we must start with an equilibrium mixture and we must have a change, right? But if we simply mix the reactant and product to get a non-equilibrium mixture, and what will be next? Like you can't predict using the Shuttle Principle, okay? Now in that case, reaction quotient comes in handy and able to solve this question to determine whether a non-equilibrium mixture will have a net forward reaction or a net backward reaction, okay? So we are going to look at these two purpose. Let's see how reaction quotient can be used to solve these problems. Now before we start, let's look at how we calculate the reaction quotient. Now looking at the equation, actually the two equations, reaction quotient, equilibrium constant, are very similar, except for equilibrium constant we have the EQM here, for reaction quotient we don't. In fact, the difference is that for equilibrium constant, the concentration of the species must be at equilibrium. So that's why we have EQM here. But for reaction quotient, let's look at the first sentence. They measure the relative amount of product and reactant present during a reaction at a particular point in time. That means it could be any point. It could be any point. It could be at the equilibrium condition. It can be at non-equilibrium condition. So reaction quotient allows us to plug in concentration from different time points. Okay? Now let's look at the first problem here. Suppose we have this equilibrium system and we know the Kc, okay, 0.1. Now suppose we have 100 cm³ of the reaction mixture with the following equilibrium concentration. So and let's just say we have two changes occurs to the equilibrium mixture. Now the first one is we add 0.1 mole of FeNO3 and Fe-iron-3 nitrate, and by adding this solid you expect to see an increase in Fe3 plus concentration. So by increasing the Fe3 plus concentration, you see because it's 0.1 mole added to the 100 cm³, so you expect to see the concentration increase from 0.1 mole per dm³ to 0.2 mole per dm³, right? Now we try to plug in the concentration at the moment where the solid has been added. So we use this equation, product over reactant. The concentration of the product, we use the equilibrium concentration simply because we are looking at the point where the solid has been added. So at that point, the equilibrium is not yet adjusted, right? Remember, it takes time. So the moment where the solid is added, the concentration of FeSCN2+ is still this one. SCN minus is still 0.5, but now Fe3 plus concentration now becomes 0.2, right? Now, when you tap your calculator, you get this answer. Now you realize that QC is smaller than KC, right? KC is 0.1, but now you got only 0.05. Now, here, we will try to say that because QC is essentially product over reactant, right? Product over reactant. So if you have a smaller QC, right? If you have a smaller QC, that means you have not enough product and too much reactant, right? And if you got too much reactant, too few product, then you will expect to see the equilibrium will shift to the product side, right? To consume more reactant and to generate more product. By doing this, you will have a bigger numerator and smaller denominator, so QC will slowly increase until QC equals to KC, where everything reach a new equilibrium. Okay, so this is how it works. So looking at here, if QC is smaller than KC, then the equilibrium position will shift to the right in order to increase the QC until QC equals to KC, right? So this is the idea. Now, looking at another situation. In this situation, we add this amount of sodium phosphate, and it turns out that Fe3 plus will react with the phosphate ion to form precipitate. So basically, the addition of this solid removes some of the Fe3 plus, and therefore bringing down the concentration of Fe3 plus. So now it turns out that it is changing from 0.1 m to 0.05 m. All right. Using a similar calculation as before, plug in those numbers. Now we get a bigger QC. Okay, a QC bigger than KC. So similar idea. A bigger QC, that means too much product and too few reactants, right? Too little reactants. So in order to consume more product and generate more reactant, we ought to do more backward reaction, right? So the equilibrium position shifts to the left to decrease the QC until QC equals to KC, right? So this is how we use the value of QC to predict how the equilibrium position changes, right? Now this diagram here is very useful. It is a number line, and you know the number on the left is smaller, the number on the right is bigger. Now KC is in the middle. If QC is smaller than KC, then all we want is to achieve KC, right? So you kind of follow the direction of this arrow, and that is pointing to the right. So that implies the equilibrium position shift to the right, right? Now, similar idea, if QC is bigger than KC, so following the direction of the arrow, the equilibrium position will shift to the left, and therefore lowering the value of QC, and therefore QC can be equal to KC, right? So now this is a quick summary, okay? Now, so this is how we use reaction quotient to predict concentration changes. Now, the second situation is where we start off with a non-equilibrium mixture. And this is the case where the Shuttle Principle has no idea what to do. Let's just say we have the same system, but this time we try to mix the three chemical species using their initial concentration as follows. Initial concentration. So we simply mix the three things together, and obviously they did not reach equilibrium at the moment that they are added into the beaker. Okay. What we try to do is to calculate the QC using this initial concentration, and you plug in those numbers, you get QC equals to 0.12. All right. Now at this moment, you compare QC to KC. Now you realize that QC is bigger than KC. Okay. Now again, QC is essentially product over reactant, right? So using a similar idea, if you have a bigger QC, that means you have too much product and too little reactant, right? So you will expect to see there will be a net backward reaction in order to consume more product and generate more reactant, okay? So if these three things are mixed together with these initial concentrations, we will expect to see a net backward reaction, or we will expect to see a faster backward reaction. Okay? Now this is why we have to learn QC, because if you use the Shuttle Principle, you have no idea how to solve this problem, simply because there is no change. There is no change on the equilibrium system. Okay? So this is again very similar to the previous number line, but pay attention. We won't say the equilibrium position shift to the right, shift to the left, simply because it is not at equilibrium. It is not at equilibrium. So how can the equilibrium position change, right? So instead of saying the shifting of equilibrium position, we will say a faster forward reaction, a faster backward reaction, or net forward reaction, net backward reaction. Okay? So pay attention to the choice of words. Okay, so let's look at a practice question at the back here. Again, pause the video and try to do it yourself, or try to at least glance through the question before I show you the answer. Alright, so let's have a look. We have an equilibrium mixture. Each of them are 0.1 mole per dm cube. The total volume is 100 cm cube. Calculate the equilibrium constant of the reversible reaction. So you know Kc equals to C squared EQM, D EQM, A EQM, as well as B EQM, right? Okay, and they are all 0.1 mole per dm cube, so essentially it's 0.1 cube over 0.1 square, right? All of them are 0.1, and that would be 0.1, okay? Mole per dm cube. Okay, so that would be the Kc. Now, with reference to the reaction quotient, without calculation, how the equilibrium position change when we add 0.1 mole of B into the mixture. So B is the reactant. So if we add 0.1 mole of B, so the reactant concentration, okay, the concentration of B increases, right? So since QC is equal to C squared over A and B, right? So we will expect to see QC decreases, right? If this one increases, QC decreases, right? When QC decreases, then we will expect to see the equilibrium position shift to, remember, a smaller QC according to the number line, right? KC is here, QC is here, so should shift to the right. They shift to the right, okay? Shift to the right. So until QC equals to KC, okay? So this is how we answer this question. Of course, if you really want to answer it, use sentence. Now part C, this time we try to use a calculation and try to determine how the equilibrium position change. Now this time we add 100 cm cube of distilled water to the mixture. So this is a dilution. So everything will be diluted by half because original volume is 100. So now you're halving the total concentration. So QC equals to, again, C squared over D, A, and B, okay? Now because they are all diluted, so you expect to see 0.05 cube over 0.05 squared, right? Because originally it's a 0.1, so by halving the concentration you get 0.05. So that will equal to 0.05, of course. So very simple calculation. Now you notice, since QC is smaller than KC, right? QC is smaller than KC. So actually following the same number line, we will expect to see the equilibrium position shift to the right until QC equals to KC, okay? So shift to the right upon this dilution, okay? Now, of course, you can always double check using the Shuttle Principle, okay? So do you remember, like for dilution, they try to shift to the position where there are more solutes, right? And you can see there are 3 mole of solute on the right-hand side, 2 mole of solute on the left-hand side, and that's why they shift to the right-hand side, okay? So the Shuttle Principle and QC both agree each other, then you are safe to say that you must be correct, okay? Down here, this question, we have given us the Kc, and the mixture is prepared by mixing this in a 5 dm cube container. Calculate the Q when they are mixed. Now this is the situation where we have a non-equilibrium mixture and we have to predict forward or backward reaction go faster. Now, so Q equals to SO2 Cl2 over SO2 Cl2. Okay? So then you plug in the concentration. Now pay attention, those are 5 dm cube and those are mole, right? So you have to divide everything by 5. Okay? So SO2 is here, 0.08. So divided by 5, you got 0.16, right? And then we have chlorine, which is 0.06 divided by 5, so we get 0.012, right? And then we have 0.4 of SO2Cl2, so it will become 0.08. Okay, if my calculation is correct, it should be like this. Then you tap your calculator, okay, 0.016 times 0.012 divided by 0.08, you got 2.4 times 10 to the power negative 3. Okay, so mole per dm cube. Okay, so in this case, you see QC, when compared to 0.078, QC is actually smaller than KC, right? So we will expect to see, that should be part B already. Okay, so I have already finished calculating part A. So part B, whether net forward or backward. So since QC is more than KC, therefore there will be a net forward reaction. Okay, so this is how we solve the problem. Okay, so it should not be too difficult. Now at the back here, this is some supplementary content, which is the limitation about the Shuttle Principle. In fact, there are some scholar keep saying that actually DSE should not teach the Shuttle Principle because there are so many limitations and sometimes its prediction is wrong. However, we see the Shuttle Principle as a very simple principle, very useful in many situations, and therefore we still have to teach this one. It's still part of our syllabus. But it is also important for us to know the limitation. So in these situations, the Shuttle Principle doesn't work. For example, the first one that is simple, when there are two or more contradicting changes. Now, simply put, if I have an equilibrium mixture, and at the same time I add one mole of reactant and one mole of product to the mixture at the same time, then how the system will respond? Actually, you have no idea, right? Because the two changes are contradicting, right? And therefore, the Shuttle Principle fails to predict. So this is the situation. Now, 2 and 3 are quite similar, related, is when your system is involving gaseous mixture and the two sides are not of equal mole, okay? This is a situation where they are in gaseous state and they are not equal moles on both sides. Now let's look at this situation. Now let's just say we have a syringe, okay, a syringe like this, okay, sealed at the mouth here, and then we have a piston here, okay, right? So we have the gas inside the mixture here. Okay, so somehow we use another syringe, okay, that is a narrower syringe, okay, and we try to, okay, inject some N2 into the mixture. So we plug in some N2 suddenly, okay. So what happens to the equilibrium system? Now, first of all, we have to know is what is the change? What is the change? So you know that by adding N2, of course, you increase the concentration of N2, right? That is the immediate change. But at the same time, because this is a movable piston, if you add some N2, you increase the volume of the gas inside, so you also press the piston back a little bit, and therefore increasing the volume of the syringe, right? Now, by increasing the volume of the syringe, you actually decrease the concentration of N2, H2, and ammonia. Okay, probably H2 and ammonia only because you add some N2 into it, right? So probably these two will have its concentration decrease. Now, so these are all the changes, right? N2 concentration increases, H2 concentration decreases as you have the volume increases, ammonia concentration decreases because you increase the volume. You see, this is the shifting of equilibrium as predicted by the Shuttle Principle on each change. Again, that shows you a contradicting situation. You can't say that there are two rights and one left and it's going to be right? It doesn't add up. It doesn't do it this way. Okay, who knows which is more significant, right? So it doesn't help. But using reaction quotient, we are able to predict, because now this is the original QC, and at this moment that should be equal to Kc. Okay, this time QC equals to Kc, because it starts out with an equilibrium mixture here. Okay, equilibrium mixture. Now we try to change the concentration into mole over volume, and that would become like this one. Simply rearranging the terms. So these will not change, right? These are somehow constant. Okay, this will not change. Okay, at the moment where N2 is injected into it. The moment N2 injected into it, these two should be not changing, right? So all we have to look at is this term, okay, which is volume and the number of mole of N2. Now, injecting the N2 will increase the number of mole of N2, but also increase the volume. So the question is whether or not this term is bigger than 1, smaller than 1, or equal to 1. If the whole term is bigger than 1, then it will make QC bigger than Kc, right? In that case, the equilibrium will shift to the left. On the other hand, if it turns out that this term is smaller than 1, so the whole term, the whole QC becomes smaller than Kc, so the equilibrium will shift to the right. Okay? So this is how reaction quotient are able to solve these involving contradicting conditions. Okay? Now, so that's it for the reaction quotient. So that's it for today. Bye-bye.